Hello everyone from Math 2200, Discrete Mathematics. This is Professor Wenson here again with a video on your ZyBooks Section 8.8. It's on solving linear homogeneous recurrence relations. Right? So a very special kind of recurrence relation. All right. So they start off here reminding you of what a Fibonacci sequence looked like. Remember, like the f sub 0 was 0 and f sub 1 was 1. These were like the bases. And then they gave you the recursive rule, right? The recurrence relation. How does one term in the sequence depend on previous terms? And for a Fibonacci sequence, every term is the sum of the previous two terms. And this is, for n greater than or equal to 2. And then they go into some history and stuff. And what we're going to be doing in this section is learning how to solve a recurrence relation. Now, what it means to solve a recurrence relation is to take a definition for a sequence defined recursively, like this is, and find an explicit formula for the nth term. Notice, that they go into throughout this section, throughout the activities. They go into how do I take this recurrence relation for a Fibonacci sequence, and these initial terms, the 0th term is 0, the f sub 1 is 1, and figure out that, oh well, obviously, the nth term, or f sub n, which would be technically the n plus first term, because they're starting at 0. The n plus first term is 1 divided by the square root of 5 times the quantity 1 plus the square root of 5 over 2 to the nth power minus 1 divided by the square root of 5 times the quantity 1 minus the square root of 5 over 2 to the nth power. Like this is pretty crazy looking. How did they figure this out? How do you figure out that when I plug in n, I'm going to get this expression back for the term of the Fibonacci sequence. And that's what solving a recurrence relation is. It's taking a recursive formula for a sequence and finding an explicit formula for the sequence. Right? Notice how this does not depend on previous terms like the recursive formula does. That's what an explicit formula was, hopefully you recall. Yeah, so like I said, finding an explicit formula for a recursively defined sequence is called solving a recurrence relation. Alright, now what they're asking you to do here is, plug in, take this just to show you that this actually works. This is actually a good, they show you that this thing works here. It's actually a good explicit formula for the Fibonacci sequence. They're telling you, hey, plug in 2 for n and see what you get. What's f sub 2? So I'm going to do that on some paper real quick. Alright, so here's that explicit formula for the Fibonacci sequence they gave us. And before I plug in 2, let me just show you that it also works, it should work for every term. If it truly is an explicit formula for the Fibonacci sequence, should work for any value of n that they gave us, from 0 upward for all the non-negative integers. So now remember, f of 0, when n equals 0, f sub 0 was defined to be 0 in those initial terms when it was defined recursively. And you see what we get here. This would be 1. I like pulling the 1 over the square root of 5 out, so I don't have to write it twice. So I pulled 1 over the square root of 5 out, and then I have this 1 plus root 5 over 2 to the nth minus 1 minus root 5 over 2 to the nth. Now I'm plugging in 0 for n, and do you see that I'll have something to the 0 power, which will be 1, minus something to the 0 power, which will also be 1, and do you see I get 0 here? Alright, I have 1 over the square root of 5 times 0. So that matches when n equals 1. Again, the way those initial terms were defined was, f1 was 1. Let's see if we get the same thing here. So it'll be 1 over the square root of 5 times, and then 1 plus the square root of 5 over 2 to the first. Right, I'm replacing n with 1. Minus, and then 1 minus the square root of 5 over 2 to the first. And this will be 1 over the square root of 5 times, and then putting these together, now you got to distribute the negative here, right? You're subtracting all that numerator. So 1 minus 1 is nothing. Then root 5 minus negative root 5 would be 2 root 5. And then you have a common denominator of 2. So this just becomes square root of 5 over the square root of 5, which all cancel, and you're left with 1. Hey, that matches as well. And then look at n equals 2, right, which is what they're asking us for. Now, hopefully, it'll be 1, right? Remember that from 2 onward, if you recall the recursive definition, every term, when I plug in 2 onward, it should just be the sum of the previous 2 terms, right? 0 plus 1, 1 plus 0. So this should end up giving me 1. And let's see. So I have 1 over the square root of 5 times, now this expression squared, right? I'm plugging in a 2, so I'm going to square the numerator, and that'll give me 6 plus 2 root 5 over 4. Right? So I squared the numerator, which would be 1 plus the square root of 5 times 1 plus the square root of 5, and then you FOIL. Right? Trust me, that's 6 plus 2 root 5. You can try that on your own. And then square the denominator, that's 4. Then minus, and same thing here, I'm going to square this, I'm putting in 2 for n. Now 1 minus the square root of 5, when you square it, that'd be 1 minus 2 root 5, and then plus 5, so 6, 6 minus 2 root 5 in the numerator, and then 4 in the denominator. And then I got 1 over the square root of 5, and then when I put these together, again, you got to distribute this negative here, subtracting all the numerator. Well, you'd have 6 minus 6 is gone. Then you'd have 4 root 5 over 4. Right, 4 root 5 over 4. The 4's cancel, the root 5's cancel, and again, I am left with 1. And it matches. It matches what we know to be the first 3 terms of the Fibonacci sequence. And if I were to plug in 3, I'd get 2, right? 1 plus 1. F sub 3 would be 2. And if I were to plug in 4, I'd get 3, 1 plus 2. This formula matches the Fibonacci sequence. It is an explicit formula. As crazy as it looks with all the square roots and whatnot, every single output, when I plug in an integer, a non-negative integer, will be an integer. Will be some term of this Fibonacci sequence. So f sub 2 is 1, right? And I mean, we know from the recursive formula that f sub 2 is 1 as well, right? F sub 2 would be f1 plus f0, so 1 plus 0. So I'm also getting 1 there. I mean, that's kind of asking the same question twice, just finding it in a different way. Right? Okay. So now let's talk about, how do we solve a recursive a recursion relation, a recurrence relation, or a recursive formula. So they start off here with an example of a geometric sequence defined recursively, and I'll actually go into the process of how we solve this, and then once we get the solution to this one, we'll use that as kind of a guide for future recursive relations. Right? So without seeing any techniques yet, after this example, we're going to see something that'll motivate a technique for solving these kinds of recurrence relations later on in the section. Alright, so we're starting off here, g sub 0 is 2, right? So the first term of the sequence is 2. And then from, when I plug in 1 onward, g sub n is 5 times the previous term, right? So the next term, so g sub 1 would be 10, right? 5 times 2. G sub 2, and then G sub 2 would be 50. Then G sub 3 would be 250, and so on, right? This is an example of a geometric sequence. Hopefully you remember that, where you to get from one term to the next, you just keep multiplying by the same number, that common ratio. And in this case, that common ratio is the number 5, right? It's just take every term, multiply it by 5, you get the next one. All right. So here's how we can solve a recurrence relation like this in a very long way. All right. This is actually this is the long way. So we know this rule. All right, we know this rule. All right. And this G sub n minus 1, now if n is greater than or equal to 2, this should be greater than or equal to 1, and then I could, say, hey, G sub n minus 1 is just 5 times G sub n minus 2, isn't it? So now G sub n for n greater than or equal to 2 is 25, 5 times 5, or 5 squared, times G sub n minus 2. And I'm going to write it this way for hopefully an obvious reason when we get through more. All right, then if n is greater than or equal to 3, just keep this going. We have 5 squared times, and then G sub n minus 2, if n is greater than or equal to 3, n minus 2 would be greater than or equal to 1, and I could apply this rule, and G sub n minus 2 would be 5 times G sub n minus 3, right? So we're getting 5 cubed times G sub n minus 3. And, this is for n greater than or equal to 3. Right? Now, what I'm trying to do here is eventually get this, I'm trying to get this subscript here down to what we know. Right? We know G sub 0. So notice after one application of the rule, I'm down to n minus 2. And then there's 5 squared. Another application of the rule, I'm down to G sub n minus 3, and it's being multiplied by 5 cubed. So I could keep doing this and say, oh, this must be equivalent then to 5. Now, just think of what would n minus what would give me 0. I'm trying to get down to the G sub 0 that we know. So this question mark would need to be n, right? I'm going down to G sub n minus n. And if I go down to G sub n minus n, or G sub 0, then there's going to be a power of 5 to the nth in front. I hope that all made sense, right? That's just applying the rule, to n times, or n minus 1 times. And then we know G sub 0. We know G sub 0. It's 2. Right? So putting this all together, we get G sub n equals 2 times 5 to the nth power. And here is an explicit formula for the sequence called G. Right, and this explicit formula would be called the solution of the recurrence relation. And you can double check it. When n equals 0, you get 2. When n equals 1, you get 10. When n equals 2, you'd get 50. When n equals 3, you'd get 2 times 125, that's 250. The rule down here matches the sequence I get when I use the recursive rule, just like that Fibonacci rule earlier. Now, what I'm going to point out here, All right, what I'm going to point out here is something we're going to use for future recurrence relations that are like this one right here. Hopefully you're noticing that this solution is exponential in n. It's an exponential function, an exponential rule. It's exponential in n, right? Meaning the variable n, right, my input variable, is in the exponent. Right? This is 5 to the nth here. And then times some constant, but the more important thing is this part right here. This exponential part of the rule. We're going to keep that in mind and use that to motivate a technique for solving recurrence relations like this later in the section. Okay. All right, so they go through kind of the same thing. Again, it wouldn't be hard to guess that the explicit formula is g sub n equals 2 times 5 to the n. All right. Then I think they go through, check that for any number c, it would work, not just 2. Like I said, the most important part of this is the 5 to the n. Any value c would satisfy this, the recursive rule. This rule would be satisfied by g sub n equals c times 5 to the n for any c. Well, any c that's, well, actually even for 0, for any c. The 2 here, right, the 2 that I got is specific to this initial condition. Right? So the recursive rule is satisfied by any exponential with 5 to the nth on it, 5 to the nth power. But then I throw in this initial condition, and now we specifically have to have the number 2 in front. But again, the most important thing behind all this is that our exponential rule, right? We have an exponential solution to our recurrence relation. All right, so I'll let you read through this, showing that for any number c, g sub n equals c times 5 to the nth satisfies the recursive rule. Right? And then they plugged in the initial condition, oh wait, okay, so if this satisfies it for any c, what about when the initial value needs to be 2? When g sub 0 needs to be 2, c needs to be 2 as well. Right? And that's another way we could have gotten our specific solution. In this procedure here, what's going on here with the, hey, plug in an exponential, see if it works, and then now that you know an exponential rule works, which specific function will work for that specific initial condition? That's what we're going to be doing for a lot of these, for actually most of the recurrence relations we're seeing here. All right. So another activity here, an example is like, hey, h sub 0 is 3, an initial condition, and the rule is another geometric, right? Another geometric sequence. Every term is 7 times the previous term. So kind of like earlier, if I went down, to hn minus 2, hn minus 3, hn minus 4, and so on, all the way down to h0, I'd have h sub n equals, 7 to the nth power times h0, so times 3. But really, it would work for anything. This, if you ignore the initial condition here, this recursive relation, this recursive rule, would be satisfied by any number times 7 to the nth power times the exponential. So that's what they're asking you here. So like, which of the expressions satisfy the recursive rule only? Well, anything times 7 to the nth. Anything times 7 to the nth. Any number. Any constant times 7 to the nth would satisfy this recursive relation. So both, h of n equals 8 times 7 to the nth, h of n equals 3 times 7 to the nth, both of these would satisfy just the recursive rule, but only one of them satisfies it and the initial condition. So which one of these satisfies the recursive rule but also has h sub 0 being 3? Well, not this first one. H sub n equals 8 times 7 to the nth. If you plug in 0, you're going to get 8, not 3. It's this other one, right? So h sub n equals 3 times 7 to the nth, but not 8 times 7 to the nth. That one satisfies the recurrence relation and the initial condition, and that's what we're looking for. Right. All right. So hopefully that all made sense. Now, this recursively defined sequence and this recursively defined sequence and even the Fibonacci sequence, these are all examples of what are called linear homogeneous recurrence relations, and they get into the definition here. And we'll see what makes a recurrence relation linear and homogeneous. Right. So I'll read this one. Right. There are many different kinds of recurrence relations, some of which are very difficult to solve. There are also recurrence relations for which there are no known explicit formula, right? Ones that haven't been solved yet. But this section, this material, focuses on a particular class of recurrence relations called linear homogeneous recurrence relations. All right, so each number in a sequence defined by a linear homogeneous recurrence relation is a linear combination of numbers that occur earlier in the sequence. All right, and that's it. Nothing more. So again, here's the specific definition, more proper definition of what they're saying here. So every term in the sequence is some linear combination of the previous terms. Now, a linear combination of numbers is a constant times one plus a constant times the other plus a constant times the third plus a constant times the fourth, etc. So here, a linear homogeneous recurrence relation of degree k has the following form. So you see the nth term, or f sub n, is equal to, and then here's what they meant by a linear combination of previous terms. See, it's a number times the term before, plus some number times the term before that, plus some number times, the k terms back, n minus kth term. And notice that's it. There's nothing else added. Every term is a linear combination of the terms before it. Some of the terms before it. I mean, maybe up to k. And if you go up to k terms back, it's going to be called a degree k recurrence relation. And all these c1 times f sub n minus 1 plus c2 times fn minus 2 plus ck times fn minus k. All these c's, the cj's, are constants that do not depend on n. They're just numbers. There's no variables in them. So c1, c2, ck, those are just numbers with no variables. All right. So like this one here, this h sub n equals 7 times h sub n minus 1. See how there's a linear combination of previous terms and that's it? Nothing else is added? And there's just a number times a previous term, plus a number times a previous term, plus a number times a previous term. That's all a linear homogeneous recurrence relation is. And this would be considered a degree 1, right? Because you're only going back one term. This one here is another degree 1, right? It's again, every term is just a number times a previous term. The Fibonacci sequence is a degree 2 linear homogeneous recurrence relation, because you see again, every term is just a linear combination of previous terms, and we're going back 2 terms. So that'd be degree 2, and again, it's just a number times a previous term plus a number times a previous term, and that's all. Right? 1 times fn minus 1 plus 1 times fn minus 2. All All right, then they get into some examples of some things that are linear and also, oh yeah, we gotta get into homogeneous as well. So again, this is linear homogeneous, right? Just every term is a linear combination of previous terms, and again, nothing else is added after this. So that makes it homogeneous. In a homogeneous recurrence relation, there are no additional terms in the expression for Fn besides the ones that refer to earlier numbers in the sequence. So again, they have it right here. So the following table below illustrates some examples. Right? So here, B. All right. So here's an example. Right? B. Say the nth term is 1 times the previous term. So far so good. Plus 1 times. Now this is the product of the set two terms ago and 3 terms ago. Bn minus 2, bn minus 3. This is not. This product of 2 previous terms makes it non-linear. Right? In a linear recurrence relation, every term only looks at 1 previous term. It's just a number times a previous term plus a number times a previous term, and so on. And there's not more than 1 previous term mentioned in each of these parts of the sum. It's just again a linear combination of previous terms. This is not a linear combination of previous terms because of this product here. Here, this one, Cn equals 3n times Cn minus 1. Yeah, there's a previous term, but look, the coefficient is not just a number. It's got 3n. Now, if it was just 3 times Cn minus 1, then it would be linear. But it's 3n, right? The coefficient depends on a variable. It's not a constant. So that's why this is non-linear. Here, dn equals, the previous term, dn minus 1, plus the term before that, dn minus 2, but that term is being squared. Again, notice back in the form for a linear homogeneous, every single one of these previous terms is to the first power. That's why it's linear. Right? Okay, so this is why that's not linear, this one, right? Because you have the dn minus 2 squared, right, raised to a power other than 1. All right, now this one's considered linear because look, every term is a linear combination of previous terms, right? 3 times fn minus 1 minus 2 times fn minus 2 plus 1 times fn minus 4. There's a linear combination of previous terms, but it's not homogeneous because of this extra term at the end that doesn't involve previous terms, right? That's just plus n squared. That makes it, non-homogeneous. So it's linear, cool, right? Degree 4, because you're going back 4 terms to n minus 4 here. But again, not homogeneous because this extra term being added. Same thing for this next one. Gn equals gn minus 1 plus gn minus 3. It's linear because you got every term is a linear combination of previous terms, and it's degree 3. But it's not homogeneous because of the extra term being added here, this plus 1. Right. All right, then finally, these last 2 examples are linear and homogeneous because every term is a linear combination of previous terms and there's no extra terms being added. Same thing for here. Every term is a linear combination of previous terms, and again, all the coefficients are constants. 2, negative 1, 2, negative square root of 3. All the coefficients are constants, and there's no other terms being added after it. All right, so you're asked to identify the following, right? So I'll just do this first couple. All right, I'll leave the third one to you. So here, fn equals negative 1 times fn minus 1 plus the square root of 2 times fn minus 5. Yeah, this is linear. All right, it's just a number, a constant times a previous term plus a constant times a previous term. It would be degree 5, right? They didn't ask about that, but it would be degree 5 because you're going back 5 terms. And there's no extra term being added at the end. So it is homogeneous. So this is linear and homogeneous. This one, you have, fn equals, a number, -1, times the previous term, fn minus 1, great, plus, and then, the coefficient on this part of the sum is not a number. It's not constant. It involves a variable. So this is not linear. And then this one would be linear but not homogeneous because of the +1. I might as well say it. Okay. Pretty easy stuff. All right. I said I'd leave the third to you, but whatever. It's pretty easy to see, hopefully. You got a linear combination of two previous terms, but then you got this +1 added on at the end, making it non-homogeneous, right? So again, we are going to look at linear homogeneous recurrence relations in this section, solving those. Now, I did the one earlier, right, where you had gn equals 5 times gn minus 1. And remember, it had exponential solutions where there was this, 5 to the n involved. So we're going to, again, use that to motivate us in the solving of linear homogeneous recurrence relations. So, hey, maybe other linear homogeneous recurrence relations have similar type solutions. So therefore, right, a reasonable starting place for more complex linear homogeneous recurrence relations is to guess that the solutions are also exponential expressions. So we're going to plug in an exponential expression, x to the nth. Now again, I know you're probably thinking, hey, that's a polynomial, that's not exponential. But remember, the variable is n, not x. The variable is n. That's the input variable for all these sequences, right? So the variable n is in the exponent. So we're going to plug in an x to the nth power, an exponential expression in n, into the recurrence relation, and that gives rise to an equation called the characteristic equation for the recurrence. All right, and if the number x satisfies the characteristic equation for a linear homogeneous recurrence relation, then x to the n satisfies the recurrence relation. All right. Now they go through an animation here, all right, showing you how to find the what's called the characteristic equation. I'm actually going to write this out, right? And we'll get what's called the characteristic equation. Will be a polynomial equation. We'll be able to solve for x. What values of x will give me a kind of solution to the recurrence relation. Okay, so here I have the recurrence rule for a Fibonacci sequence. And again, hopefully you recognize it as linear homogeneous. Right? Every term is a linear combination of previous terms, right? And there's no other term being added after. So this is another example of a linear homogeneous, and it's degree 2, because you're going back to n minus 2. You're going back 2 terms. Now, since it's linear and homogeneous, what we're going to do is I'm going to plug in an exponential expression. Say fn equals x to the n. All right. Again, the variable here is n. That's why it's exponential. All right. So I'm going to do that. So fn, we said, is x to the nth. All right, x to the nth. So if that's f sub n, right, the function with the input of n, then f sub n minus 1 would be x, is replace n with n minus 1, would be x to the n minus 1 power. Plus, and then f sub n minus 2, if this is f sub n minus 2 would be x to the n minus 2. Right. And then we solve this for x. Now, what I'm going to do is put it in a standard form for a polynomial equation. So I could take everything to one side. You have x to the nth minus x to the n minus 1 minus x to the n minus 2 equals 0. Okay. And then you can factor every single one of these, the lowest power on any of these is x to the n minus 2. I can factor that out. Take out x to the n minus 2 times, and then if I pull out x to the n minus 2 and use some rules of exponents, you'd have x squared for the first term here, because x to the n minus 2 times x squared would be x to the nth, minus, and then x to the first, right? X to the n minus 2 times x to the 1 would be x to the n minus 1, and then minus, and then you're pulling this whole term out, so you just have 1 left over there, equals 0. And again, it's just like a polynomial equation where we're trying to solve for x. Here, I should have written that up here. All right, we're trying to solve this thing for x. Figure out what are values of x that make this type of exponential rule a solution to this recurrence relation. Now, if you recall, there is the zero product property. The only way a product is equal to 0 is if any of the factors is 0. So either x to the n minus 2 is equal to 0, or x squared minus x minus 1 is equal to 0. Now, one of these is going to be unimportant. The only way this is going to be working out here is if x is 0. All right, this implies that x equals 0, and that leads us to what's called, the trivial solution. F sub n equals 0 to the nth power. Fn equals 0. And, Fn equals 0 works. I mean, you'd have 0 equals 0. If every single term of the sequence is 0, then this is satisfied. If every single term of the sequence is 0, right, let me show you. That would be f0 is 0, f1 is 0, f2 is 0, f3 is 0, f4 is 0. Then definitely every term is the sum of the previous two terms. So this is called the trivial solution. It'll obviously work. It obviously satisfies this, but it's uninteresting. It doesn't tell us anything. All right. So again, this trivial solution is uninteresting. We're going to ignore it. All right, ignore. So the other one, right, the other factor with this degree 2 polynomial, this is much more interesting. X equals 0 is not a solution to this one. And this other factor without the x to the nth whatever equals 0, where the trivial solution isn't the solution, this is called the characteristic equation for this recurrence relation. All right, this is called the characteristic equation for our recurrence relation. All right. So again, just ignoring the trivial solution, because really for any linear homogeneous recurrence relation, if the sequence was all zeros, the rule would be satisfied. But again, that's not interesting at all. All right. So, and then we'll get into solving for x. We'll do this in another example. I'll come back to this. All right, but that's the first step we're going to do in solving a linear homogeneous recurrence relation. Is plugging in an exponential rule. So suppose the sequence f is an exponential, and then trying to figure out what values of x will actually satisfy the rule. Right? You plug in the x to the n power thing and get this characteristic equation. And one thing you're going to notice, hopefully, and I'll point it out here, whatever the degree of the equation is, of the relation is, whatever the degree of the relation is going to be the degree of the equation, right? This is a degree 2 polynomial equation, a quadratic, and the homogeneous relation was a degree 2 relation. So that should happen, right, if you're doing this properly. And they go through the animation here and show you the same thing I did. Well, they did it in a little different step, but show you basically the same thing. All right, so they're asking you in this next activity is just match each relation to its characteristic equation. All right, so I'm going to do this one more time with, I'll pick one of these here, say this one. All right, and I'll put it up on paper and do it. Find the characteristic equation corresponding to that relation. So again, I have a degree, it's another linear, homogeneous, degree 2. So when I eventually end up writing the characteristic equation, it's going to be a quadratic equation, right? A degree 2 polynomial equation. So I'm going to plug in. I'm going to assume that f sub n. I'm going to assume that the sequence is some sort of exponential, x some base x to the power n. And if that's the case, I've got f sub n minus 1 here. Then would be x to the n minus 1, and f sub n minus 2 in here would be x to the n minus 2, and do all these replacements. So we have x to the nth equals negative 2 times x to the n minus 1 minus 2 times x to the n minus 2, and then again I'm going to take everything to one side, 0 on the other, do some factoring. So we have x to the nth, plus 2x to the n minus 1 plus 2 times x to the n minus 2 equals 0. And again, all these have a common factor of x to the n minus 2. I'll factor that out. And then you'd have x squared, right, to give me x to the nth plus 2x to the first. That would give me x to the n minus 1 if I distribute. Then plus 2 is equal to 0. And again, we can ignore this. I can ignore this because, if I set this equal to 0, it's going to give me fn equals 0. And that was that trivial solution, right, where every single term in the sequence is 0. So the characteristic equation here, I'll just put char equa, right? Char equa. The characteristic equation is, when is x squared plus 2x plus 2 equal to 0? All right. So going back to this activity here, that's just this one. Come on, get down there. All right. And then notice I'll do one more of these out loud without writing it. We have fn equals, fn minus 1 plus fn minus 5. So you see there's this would be a degree 5. It would be one of these 5th degree polynomial equations down here. So now I'll tell you right now, the nth term, the fn, that'll be the x to the 5th. And then subtract 1, meaning this will be the x to the 4th term. Subtract 5, meaning this will be the constant. This will just be 1. So I have x to the 5th equals x to the 4th plus 1, or, taking everything to one side, x to the 5th minus x to the 4th minus 1 equals 0. All right, just kind of skipping ahead and thinking about it out loud. Just moving this down. Oh. Yeah, there you go. So again, the fn will be that power still will be degree 2. This will be the x squared term, and then this is n minus 1, so x to the first term, n minus 2. This will be the constant. So x squared equals 2x plus 2. And take everything to one side. Then again, this will be the x to the 5th term. Then minus 4, x to the first term, and then the constant. So you have x to the 5th equals x plus 1. And then take everything to one side. Hopefully you get the hang of that. All right, you don't have to write it out all the time like I did. All right, then like I said, now we're going to be solving. Once the characteristic equation has been determined, the next step is to find all the values of x that solve the equation. Since the characteristic equation is, some polynomial equation, the goal is to find the roots of a polynomial, right? Some polynomials have complex roots. This material, with imaginaries, we're not going to cover that. in this section, right? This material only covers the case where the characteristic equation has real roots, so they're being kind of nice to you here. Right? So we first consider the case where all the roots are different, right? Where every root is distinct. Hopefully you remember back to like a pre-calc or algebra class. This means that we're going to look at the first case is we're going to look at the case where every single root, every single solution has a multiplicity of 1. Right? It shows up one time, has one factor that it makes 0. Alright, and we saw this one earlier. Right? This was the characteristic equation for our Fibonacci sequence. Right? X squared minus x minus 1 equals 0. And if you use the quadratic formula, right, this is quadratic, you get 1 plus the square root of 5 over 2 as one value of x, and 1 minus the square root of 5 over 2 as another value of x. Right? And both of these satisfy the recursive relation. And then a fact that they'll prove here, if you have if you know some solutions to a linear homogeneous recurrence relation, then any linear combination of those solutions also satisfies the recurrence relation. So you see an Fn equals, some constant s times x to the nth, where x is 1 plus root 5 over 2, plus some constant t times x to the nth again, where this time x is 1 minus root 5 over 2. This will be the general solution to our Fibonacci sequence, our Fibonacci recurrence relation. And then you have to go and, figure out what S and T are using the initial conditions, right? Sure, this is the general solution, but then you have to find what are the constants that satisfy the initial conditions. That F0 was 0, F1 was 1. Right, but right now, I'll just state the theorem for you. You can read the proof. So if G sub n and H sub n satisfy a linear homogeneous recurrence relation, then so does, some number times G sub n plus some number T times H sub n. Basically, any linear combination of those solutions is also a solution to the homogeneous linear recurrence relation. And again, they go through the proof down here. Please read it over. Hopefully it makes sense. All right. And then they say, okay, now that we have the general solution, the final step is to use the initial values to find the exact linear combination that satisfies the recurrence relation and the initial values. So I'll let you read through this one here. They plug in, they say, hey, when n is 0, remember we need f0 to be 0, we need f1 to be 1. So they plug in 0, they plug in 1, and then they get a system of equations involving the constants and solve for them. And that's where that crazy formula came up earlier, where it was, the nth term, f sub n, was 1 over the square root of 5 times 1 plus root 5 over 2 to the nth, plus, negative 1 over the square root of 5 times 1 minus root 5 over 2 to the nth. That's how they found that, going back to the very beginning, that's how they found this explicit formula for our Fibonacci sequence. Found the characteristic equation, solved the characteristic equation, had a general solution, which was a linear combination of the two solutions from the characteristic equation, then plugged in the initial conditions, the f0 equals 0, f1 equals 1, and found those constants, the 1 over root 5 and negative 1 over root 5, that gave me this linear combination of the solutions from the characteristic equation. It's a lot of steps, but it does give us an explicit formula for the Fibonacci sequence. All right, so I'm going to go back down to where we were, which wasn't that far. There we go. So I'll let you go through, I'll play that animation and go through the activity. And I guess, one of these, the 1 plus root 5 over 2, they mentioned that is what's called, that's the golden ratio, about 1.618. Comes up in art and science a lot. Whatever. All right, you can read that if you want. All right, so let me show you an example. All right, I will go through this example here on paper, and they have all the steps listed out here, but I want to do it for you on paper, show you one at a time, and you can read the steps later if you wish as well. Okay, so here's the sequence they're giving us in this example. So, the first term is 7 when f is at 0, when the input's at 0. The next term is 0, the next term is 10, right? So these are the initial values, right? These are the initial values. And then we have our recurrence relation. Right, the recursive rule. So you see that every term from here on out is twice the previous term plus the term before that minus twice the term before that. Okay. So if you want to start right now, there's f0, here's f1, here's f2. F3 would be 2 times the previous term, 2 times f2, so 20, plus f1, so 20 plus 0, so 20 still, minus 2 times f0, so minus 14. 20 minus 14 would be, the next term of this sequence would be 6. There's f3, right? f sub 3. And then I'll do one more, f sub 4, and then we'll go into actually solving. I just want to show some examples. And you've seen this before, right? Now f4, replacing in with 4, would be 2 times f3, so 12, plus f2, so plus 10, that'd be 22, and then minus 2 times f1, so minus 0, so 22. The f4 is 22, and so on. I can keep going like this, right? I can keep doing that forever and ever and ever. What I want to try to do, though, is instead of using this recursive rule for the sequence terms, I want to find an explicit rule. So step 1, and I'll put some step numbers here. Again, this is a linear homogeneous. This procedure we're going through here is only good for linear homogeneous recurrence relations, and that's all we're seeing really in this section. So this is linear and homogeneous, I'm noticing. So step 1 is find that characteristic equation. The characteristic equation for this recurrence relation. So remember, I replace f sub n with x to the nth. And if I did that, remember this is a degree 3, I'm going back 3 terms. This would end up being the x cubed term equals, and then n minus 1, so 1 degree less. This is 2x squared then, plus, and then this is going back 2 terms, so 1 degree less than that, so plus x, minus, and then going back 3, this is the constant term, so just minus 2 times 1. And putting everything on one side, we have x cubed minus 2x squared minus x plus 2 equals 0, right? So I establish this characteristic equation, a degree 3 polynomial equation. Step 2, solve this. Solve it. Right? Solve the characteristic equation. Now, this is a degree 3 polynomial. Right? There is a cubic formula, kind of like there's a quadratic formula, but it's crazy and nobody remembers it. Nobody memorizes it because it's not. It's too big. It's too much. So I'm going to try factoring. Right? Now this one's a nice one. You can actually factor it by grouping. Right? If you look at the first 2 terms, that's x squared times x minus 2. And if you look at the next 2 terms and pull out a negative 1, you'd have minus the quantity x minus 2. And then you look at both halves here. Both these products have x minus 2 in common. So you got x minus 2 times, and then what's left over would be x squared minus 1. And now we have x minus 2 times x minus 1 times x plus 1, right? This is a difference of squares. And so we have 3 distinct solutions, right? We have 3 distinct, meaning different, right? Each one of these solutions would have a multiplicity of 1. We have 3 distinct roots. We have x equals 2, x equals 1 and x equals -1. Right? So this leads me to, 2 to the nth, right? Because remember, where we're using x to the nth, fn equals x to the nth power here. So 2 to the nth, 1 to the nth, or just 1, and -1 to the nth. Again, this is just going to be 1 all the time for any n. These are solutions. These are solutions. These satisfy the recurrence relation. I'll just say they satisfy the recurrence. So if you were to go, 2 to the nth is equal to 2 times 2 to the n minus 1 plus 2 to the n minus 2 minus 2 times 2 to the n minus 3, and that'd be true. And 1 equals 2 times 1 plus 1, which is 3, minus 2 times 1. 1 equals 1. Obviously that one works. And -1 to the nth. -1 to the nth is equal to 2 times -1 to the n minus 1 plus -1 to the n minus 2 minus 2 times -1 to the n minus 3. All three of these satisfy the recurrence, and you can check that if you want. So then third step is write the general solution to the recurrence. All right, write the general solution to the recurrence, the recursive rule. And that would be Fn is a linear combination of these. Is a linear combination of these guys here, right, that I found from the characteristic equation. So Fn is going to be, some constant, say C1 times 2 to the nth plus some constant times, 1 to the nth, or just 1, plus some constant C3 times -1 to the nth. Okay, so this right here, this is the general solution to the recurrence. So if I were to plug this into the recurrence, it would satisfy it. If you were to plug in, keep plugging this with n, plug in this where you replace all the n's with n minus 1's here, replace all the n's with n minus 2's and plug it in here, replace all the n's with n minus 3's and plug it in here, and this would be a true statement. And I'm not going to do all that. All right, you got to just trust based on the proof earlier. Right? If hopefully you've read through that proof, or you take the time to read through the proof of that. Linear combinations of solutions are also solutions to homogeneous linear recurrence relations. All right, and now that I have the general solution to this recurrence, I now want to find what specific solution. What are the values of C1, C2, and C3 so that these initial values work as well? All right, so that'll be the final part. So you find the specific solution to the recurrence, and this is it. Find the specific solution using the initial values, right, or those basis values, those base cases, whatever you want to call them. And this will be the end. All right. So here is my general solution. All right, from step 3, this C1 times 2 to the nth plus C2 plus C3 times -1 to the nth. And remember those initial values. And I'll write them again here. Remember they said that F0 was 7, F1 was 0, and F2 was 10. All right. So when n equals 0, basically each one of these is going to give me an equation involving C1, C2, and C3, and then I solve that system of equations. All right, so when n equals 0, well, the left side is going to be 7, right, because I'll have f0, and f0 is 7, equals, c1 plus 2 to the 0, c1 times 2 to the 0, but that's just c1, because anything to the 0 power is 1, plus, c2 times 1, so plus c2, and then negative 1 to the 0 is also 1, so then plus c3. Right, so there's one equation involving c1, c2, and c3. When n equals 1, and just plugging in 1 for n in my general solution, you get f1. Well, f1 is 0, so 0 on the left there, and 2 to the 1 is 2, so I got 2 times c1 this time. Still plus c2, still plus c2. And then negative 1 to the 1 is negative 1, right? So minus c3. And then finally, for the third equation involving c1, c2, and c3, I plug in 2 for n. Let me pull this up a little more. Right. I plug in 2 for n, and then the left side, f2 is 10. And then, plugging in 10, again, 2 for n. 2 to the second is 4, so I got 4c1 now. And then plus c2 each time. And then, negative 1 to the second, right? I'm plugging in 2 for n. Negative 1 to the second is positive 1, so plus c3. And then you solve this system for C1, C2, and C3, and you'll have your specific solution. Now I'm going to show you a quick way of solving the system on a calculator. Now you've seen systems of equations, I'm sure, in an algebra class. You could solve this with elimination or substitution, but I'll show you a much quicker way. And hopefully you can remember this. Come back to the video multiple times if you haven't seen this before. Now, those of you that have taken a linear algebra class, know exactly what I'm talking about here when I do this. But all right, so I got my TI-84, 83, 84 are very similar. So if you want to very quickly solve a system of linear equations, make sure it's set up like this, where all your terms without variables are on one side, and all the terms with variables are on the other. And they're nice and lined up like I have here. So I'm going to make what's called a matrix. All right. I'm going to make a matrix that represents this system. And a matrix is just a rectangular array of numbers. All right, so down the columns, down the first column, I'm going to start putting in this side here, the side with the variables first. Down the first column, I put just the coefficients of the C1s. So 1C1, 2C1, 4C1 down the first column. Down the second column, the coefficients of the C2s. So 1, 1, 1. And down the third column, the coefficients of the C3s. 1, -1, and 1. Again, make sure things are lined up. And then I'll put a little bar here representing the equal signs. You're not going to see the bar on the calculator, but I'll put a little bar here representing the equal signs. And then down the last column, the constants, 7, 0, and 10. Now this is a 3-row, 4-column matrix. This would be called a 3x4 matrix. 3 rows, 4 columns. Right. I'm going to go and enter this. So above the X inverse button, there's a thing that says matrix. I go second, hit that little inverse button, go to the matrix menu. Then I want to make one. Right? So I go over to edit, enter on edit. Now, first thing you enter is the size. How many rows, how many columns? Like I said, this is a 3-row, rows are horizontal, 4 columns, columns are vertical. 3x4 matrix. And then you put in the entries. So across the top row, I've got 1, 1, 1, 7. So again, that just represents C1 plus C2 plus C3 equals 7, that first equation. Across the second row, I've got 2, 1, -1, and 0. And that just represents, again, 2C1 plus 1C2 minus 1C3 equals 0, the second equation. The third row, I've got 4, 1, 1, 10, and again, all that represents is 4C1 plus 1C2 plus 1C3 equals 10, the third equation. All right, I'm going to get out of there, go quit. And then we're going to put this into a form called reduced row echelon form. All right, reduced row echelon form. But again, I'm going to have the calculator do it. I don't want to get into all the procedure of like things called elementary row operations. So I want to put this into what's called reduced row echelon form. I don't even care that you know the name of the form. It's called RREF. All right. And on your calculator, go back to that matrix menu. Back to that matrix menu. Go over to math. I'm going to scroll up because it's pretty far down and go to the bottom of the list. See RREF. Now I know there's an REF. Don't confuse them. All right, there's R. I want RREF. And then in parentheses, I put the matrix that I want to put in this RREF form. So back to the matrix, and then under names, you see this matrix A was the 3x4 matrix I made earlier in edit. Enter on that, close parentheses, hit enter, and then here's what I'm getting. And I'll write it down. Right, down the first column, 1, 0, 0. Then 0, 1, 0 down the second column, 0, 0, 1 down the third column. And then again, I'm gonna put a little bar here for where the equal signs are. Then you have 1, 2, and 4. So again, what does this mean? Remember, these are the coefficients of C1. These correspond to the second column, C2, the third column, C3. Then you have your equal signs and then constants. So this first row now tells me that C1, 1C1 must be equal to 1. The second row tells me that C2, right, 1 in the middle here, the second column, equals 2. And the third row tells me that C3 equals 4. And then I put these in to my general solution. All right, there was the general solution. So here is the solution, the specific solution. We'd have Fn equals, C1 times, 1 times 2 to the nth, so just 2 to the nth, plus C2 times 1. Well, C2 is just 2, so just plus 2. And then plus C3 times -1 to the nth. Well, C3 is 4, so plus 4 times -1 to the nth power. Here we go. I am finished. This is the specific solution to the recursion that we were given. So I'll bring it back up. Right, here it was. Right, here it was. Sorry, I'm folding some papers right now. So look, there was the recursion we were given. All right, F0 is 7, F1 is 0, F2 is 10. There's the rule. Now, let's test this out. Let's test this out. Is this really a good explicit formula? Is this the solution to what they gave me? Well, how about F0? Well, F0 would be 1 plus 2 plus 4 would be 7. Hey, that works. F1 would be 2 plus 2, and then, -1 to the 1 is -1, so -4. Hey, that's 0. That's so far so good. F2 would be 4, right? 2 squared plus 2, and then plus 4 again. That's 10. Hey, 7, 0, 10. Working out, working out. Oh, let's do one more. What's F3? Now 2 to the third is 8, plus 2, and then -4. That's 6. All right. Look at this. And bet you dollars to donuts, the next one's 22. And then after that, whatever it is, but this is our specific solution. This is an explicit formula telling me the terms of this sequence that was described to me. Right, so one more time through the steps, and I'm going to do another one of these in a second. Well, in a few minutes, we'll talk about another situation that could come across. So again, 1, get that characteristic equation. Plug in x to the nth for fn, and x to the n minus 1 for fn minus 1, and x to the n minus 2 for fn minus 2, whatever. Characteristic equation, solve the characteristic equation. All right. And then, like I said, this was a scenario where all our solutions were different. None of them repeated. The next example I'm going to talk about is when there are repeated solutions. Then, get your powers, those to the nth power. And then the general solution is a linear combination of those. Then you plug in your specific, plug in your initial values, get a system of equations, solve that system of equations, get your specific solution. It's a lot of work. It is a lot of work, but the final result is very nice. Right? A nice explicit formula for the terms of that sequence. Okay. So back to the website. All right, so then they talk. All right. So again, you can read through the same steps. They do the same steps I did. All right. All right. They used A1, A2, and A3 instead of C1, C2, and C3. My apologies. Doesn't matter what you call them. All right. All right. So again here, if this was the characteristic equation, you'd have some, 3 to the nth and negative 2 to the nth, and some linear combination of those. So like this guy here would be a solution, a general solution to the recurrence. And then you'd go specifically, and then they say, hey, now what if if in the previous one, what if g of 0 was 1? Well, then you'd have 1 equals, s plus t. 1 equals s plus t as an equation involving s and t. And then if g of 1 was 3, then you'd have 3 equals, plugging in 1 for n, 3 minus 2t. 3 equals 3s minus 2t. Right. It's plugging in the initial values. So you get a general solution, then plug in those initial values, get a system of equations, solve that system and all that, and you find a specific one. Now comes the part where, what if we have the same solution to the characteristic equation multiple times? Right? What if a solution has a higher multiplicity than 1? So here, consider a recurrence relation, this guy here. The characteristic equation will look like this. And you notice that 2, x equals 2, is a solution twice. A multiple root. So 2 is a root of that polynomial with multiplicity 2. Right? It shows up twice, 2 factors. Now we already know that 2 to the nth would work, right? From earlier section, part of the section. Since 2 is a root of multiplicity 2, g equals n times 2 to the nth also satisfies the recurrence relation. And they show that here. So what you're going to be doing with roots that are multiple, repeated roots, is you start off with that root to the power n, and then just throw on powers of n until you get the enough solutions to equal the multiplicity. So if it has a multiplicity 2, you should get 2 solutions, like 2 to the nth, and then n times 2 to the nth will be independent, right? And also satisfy, and you can verify that. And then if it was, if it had multiplicity 3, you'd use 2 to the nth, n times 2 to the nth, and then n squared times 2 to the nth. You just keep adding higher powers of n on front until you get the same number of solutions as the multiplicity. And they explain that all down here. All right. So again, I'm not going to go into why this is, just explain that, hey, just do this. All right. In general, if the characteristic equation for a linear recurrence relation, is some polynomial equals 0, and the polynomial has a root x with multiplicity m, then all these expressions here satisfy the recurrence relation. X to the nth, then n times x to the nth, and n squared times x to the nth would also work, all the way up to n to the m minus 1 power times x to the nth, right? And this gives me a total of m different solutions coming from that root. Right? But you just keep throwing in powers of n until you get that number of solutions with that root. Let me show you an example down here, and I'm going to do my own example. All right, I'm going to do my own example, and this one's just match each characteristic equation with its general solution. So like here, if the characteristic equation was x, had x minus 3 to the fourth equals 0, then 3 would be a solution 4 times. So you'd have 3 to the nth, n times 3 to the nth, n squared times 3 to the nth, and n cubed times 3 to the nth as solutions, and then your general solution would be a linear combination of those. So you're seeing this a1 times 3 to the nth, a2 times n times 3 to the nth, plus a3 times n squared times 3 to the nth, plus a4 times n cubed times 3 to the nth. So this one here would correspond to a general solution of this second option. All right. And I'm going to actually do an example in a second. I'm actually going to go through one of the additional exercises with you that has a multiple root and show you how to work it. Okay, so let's go to, now I'm going to go to one that I don't think I assigned you that actually has a multiple root. I think it was I here. Yeah, this one has a multiple root. So again, don't do what I just did and look at the solutions. All right, but I just want to make sure something had a multiple root so I can show you how to work them. All right, so I'm going to look at number 883, part I, and we're asked to solve, this recurrence relation. So I'll go to some paper and do that. Okay, so here's the 883 part I. So again, we have our initial values here. B0 is 6, B1 is 7, B2 is 17. And here's our recurrence relation. That every term is 5 times the previous term, minus 8 times the term before that, plus 4 times the term before that. And you could list off some other terms if you want to find B3, B4, B5, whatever. But so first the characteristic equation. So I'm going to have fn equal x to the nth, and that would lead me to the characteristic. Now this one will eventually end up just being x cubed, and then this will be the x squared term, 1 degree less, right? 5 times x squared minus this will be 2 degrees less, so 5 times x, or 8 times x, and this will be the constant term with the n minus 3 here, plus 4, and then taking everything to one side, here is our characteristic equation, x cubed minus 5x squared plus 8x minus 4 equals 0. Alright, now this polynomial here it doesn't look like it's factorable by grouping like the last one. So hopefully you remember how to solve polynomial equations with integer coefficients, right? All the coefficients are integers, 1, -5, 8, -4. I can use that rational root theorem, rational zeros theorem. Remember, if this has any rational solutions, the numerator is going to be some factor of -4, and the denominator is going to be 1 basically. So I'm going to check, by the rational zeros theorem, or rational root theorem, and this is going back to like pre-calc 1. Let's check, and I'll do it by synthetic division. I'll check these values, plus or minus 1, plus or minus 2, and plus or minus 4, right? The factors are -4 basically. All right. Now I'm going to kind of do this real quickly out loud. Now if let's see, 1 minus 5 is -4. 8 minus 4 is +4, so 1 will work. So here's some synthetic division. The way I do it, you got 1x cubed, -5x squared, +8x, and -4. And I'm telling you right now, 1 will work. Remember, you drop the first one here. 1 times 1 is 1, plus -5 is -4. 1 times -4 is -4, plus 8 is +4, and then 1 times 4 is 4, plus -4 is 0. And then this line tells me how to factor that polynomial. Right, or you could have just divided by x minus 1 using law and division, right? But either way, now we have this is x minus 1, because 1 is a 0. 1 makes this equal 0, times x squared minus 4x plus 4. And then this factors to the same factor twice. This is x minus 1 times x minus 2 squared. Alright, so my solutions, my roots, are x equals 1 and x equals 2, but x equals 2 is repeated. X equals 2 has a multiplicity of 2. Alright, so then from this, we know that 1 to the nth power, or just the number 1, it satisfies the recurrence relation. And that's obvious. If fn was 1, or I'm sorry, if bn was 1, I should say bn, not fn, way back here, bn. If bn was 1, you'd have, every single one of these would be 1s. You'd have 1 equals 5 times 1 minus 8 times 1 plus 4 times 1, and that's true. 1 equals 5 minus 8 plus 4. Right? Negative 3 plus 4 is 1. So this 1 satisfies the recurrence relation if bn was just 1. And then from this, and again, x equals 2 with multiplicity 2, we'd get 2 to the nth also satisfies, but also n times 2 to the nth. Alright, both of them. And you could check, plug in 2 to the n here, 2 to the n minus 1 here, 2 to the n minus 2, 2 to the n minus 3, and see that it works. And then plug in n times 2 to the nth here, n minus 1 times 2 to the nth, n minus 1 here, n minus 2 times 2 to the n minus 2 here, and n minus 3 times 2 to the n minus 3 here, and you can see that it works. So again, I'm not going to go into all that. And if it had multiplicity 3, then I'd also have n squared times 2 to the n, but it's only got multiplicity 2, and so on. Whatever the multiplicity is, that's how many basic solutions you should get out of that. Alright, so then our general solution. Right, so then the general solution to that recurrence, to this statement here, before I get to the initial values, would be bn equals, again, I like to use c's for constants, right? So c1 times 1, right, or 1 to the nth, but 1 to the nth is always 1. So c1 times 1 plus constant c2 times 2 to the nth plus, and then c3 times n times 2 to the nth. So again, just a linear combination of these solutions to the recurrence gives me my general solution. Alright, now I'm not done. I'm just boxing it in because this is what we're going to plug our initial values into, because I want to find C1, C2, and C3 so that those initial values are satisfied. Right, so again, I'll write up what the initial values were, and we'll make a system of equations involving this C1, C2, and C3. Alright, so we were given that B0 was 6. So that'll lead me to this equation. When I plug in 0 for n, we get 6 equals C1 plus C2, and that's it. Because if I plug in 0 for n, this last term will be 0. Alright, then we were given that B1 was 7. And that leads me to this. So I'm plugging in 1 for n. Everywhere there's an n, I plug in 1. B1, 7. C1 again. 2 to the first is 2, so plus 2C2. And then 1 times 2 to the first is just 2 again, so plus 2C3. And then B2 was given as 17. Alright, so this leads me to this equation. We have 17 equals, I'm plugging in 2 for n. So 2 to the 2 is 4, so I get C1 plus and then 4C2. And then here I have, again, 2 for n. So 2 times 2 to the 2, 2 times 4 is 8. So plus 8C3. All right, and then as before, I'm going to pull up my calculator. Right, now you could probably, again, solve this by hand if you want, but I'm going to be making another, there's 3 columns here, a column there, so 4 columns and 3 equations for the rows. So it's another 3 by 4, 3 rows, 4 columns matrix. So I'm just going to go back to that matrix menu I had, edit, and just change that same 3 by 4 matrix that I had, where the first row will be the first equation. So again, the coefficients of C1, then C2, then C3, then equals, and then the constant. So 1106. So 1106 for the first equation, then 1227 for the second equation. Alright, then 14817 for the third equation, third row. 14817 for the third one. All right, then get out of there, and then the last thing I entered was reduce row echelon form REF, so I can just go second entry and re-enter it. All right, so I'm getting C1 must be 13, C2 must be -7 from the second row there, and then C3 must be 4. And plug those in, and we got our specific solution to this recurrence relation. Bn must be equal to 13 plus C2, so -7 times 2 to the nth, and then plus C3 times n times 2 to the nth, so plus 4 times n times 2 to the nth. There we go. And there's a specific formula, and let's test it out. Let's test it out. Remember our initial values here. I'll just test it with the initial values. What's B0? That'd be 13 minus 7 plus nothing, which is 6. Check. That gives me B0. B1 would be 13 minus 14 plus 8. So -1 plus 8 is 7. Check. B1 is 7. And B2, and again, this would work for any other term in the sequence, but B2 would be 13 minus 28. Right, 7 times 4 plus, and then again n is 2, so 8. 4 times 8 plus 32, and that's 13. -28 plus 32 is 4. 13 plus 4 is 17. Hey, look at that, it's matching. This is matching every term in my sequence so far, and it would for B3, B4, B5, B6 forever and ever. Okay, but we have found our specific, our specific solution, right? This explicit formula for the terms of the sequence that was described all the way back here, right? All the way back by this description here. All right, so again, characteristic equation. Solve it. Find solutions. Write a general solution involving those solutions that you got from the characteristic equation. If anything has a multiplicity higher than 1, you're just going to keep adding on higher powers of n. Attach higher powers of n to that exponential until you get that same number of solutions coming from that. Right? If multiplicity is 2, I should get 2 of them. If multiplicity is 3, I should get 3 of them, and so on. Write your general solution, then plug in your initial values, get a system, solve that system, and then you got it. All right. Again, that's a lot of work. I get it. All right. It's a lot of work, but if you do everything right, it'll work out real nice. You get a nice explicit formula for a sequence defined recursively. All right, and that's it for this section. All right, a bit of a longer video here, about an hour and a half. Hopefully I explained things well in those couple examples I did. I didn't really look at all the activities too well. I didn't play any of the animations for you, but I'll leave that to you. Alright, so hopefully this video helps you when you're working through this on your own. Again, please don't look at the solutions right away when you're looking at these. Please try to work them out before you look at the solutions. And I would also recommend trying all the problems. I know I didn't assign all of them. I would still recommend trying all the problems just to get get the hang, get more exposure to the material, get the hang of it better, hopefully. And if you have any questions, of course, send them my way. Let me know. And thank you very much for watching.